great. So we have all from the Weizmann Institute to tell us about this purple thing.
Okay, so the title of this talk is PCPs of subconstant error via Derandomized direct product, or at least until we come up with a better title. And this is joint work with Iridinur. The talk will go about as follows. We will start with an introduction. Just a second, and move the mouse. Okay, so we'll start with an introduction in which I'll say what this work is all about and why is it interesting and what is the context. And then I'll go to direct product PCPs, which is part of the title. So I'll explain what are they and why are they interesting and what is this approach. And then finally, after a long introduction, I will get to the construction of PCPs. And if time allows and you won't be too tired, then I'll get to an axiomatic approach, which means that, in fact, our construction can be generalized to a family of PCPs, the family of all PCPs that satisfies four basic axioms. And I will get to that if you will want and will have time. Okay. So just to review what a PCP is. So a PCP is a proof system that allows verifying that some claim holds by reading only few symbols from some auxiliary proof. Or a little more formally, a PCP verifier is a machine that that takes as input some string X, and it is supposed to verify that the claim that this input belongs to some language L. And when I say that it needs to verify it, I mean first that, and another thing before, that the verifier also gets oracle access or random access to some auxiliary proof string. And it is required that if the claim holds, if the string X does belong to the language L, then some proof convinces the verifier that the claim holds. And on the other hand, if the claim is false, that is, if the input is not in the language, then no matter what proof is given to the verifier, it rejects with high probability, or in our case, in our definition, it accepts with small probability. And the main feature of PCPs versus other proof systems is that it makes only few queries to the proof string. Now, I should say that unlike the input, which is a binary string, the proof string may be over a larger alphabet. And I will get to that in a second. So what are the parameters that we are interested in PCPs? We are interested in the query complexity. How many queries is the verifier allowed to make to the proof? And in the soundness error, what is the maximal probability that the verifier may accept false claims? We are interested in the proof length. How long should be the proofs that are needed to convince the verifier to accept correct claims? And we are interested in the proof alphabet. And in particular, how large should the proof alphabet be? So we wish the query complexity be as small as possible, and the same for the soundness error, and for the proof length, and for the proof alphabet. And then we have the PCP theorem that says that for every NP language, we can construct a PCP verifier that has constant query complexity, constant soundness, constant alphabet size, and polynomial proof length. Okay, so now ever since the PCP theorem, there have been a few research directions trying to improve the theorem. And in this talk, I will discuss one such research direction. The research direction that tries to reduce the soundness as much as possible, to decrease it. And in this research direction, well, we wish to decrease the soundness as much as possible. And ideally, we wish it to be a sub-constant function of the input length. And while we do that, we wish the query complexity to be constant. And ideally, we want it to be 2, which is the best possible. And we also wish to maintain polynomial proof length, L. I'll just say that this research direction is particularly useful for hardness of approximation results, that is, to obtain tight hardness of approximation results. And for this kind of results, it is particularly important that the query complexity will be 2. Now, since we wish to have all those three requirements, we have to compromise on the alphabet size because it is easy to show that the soundness must be at least 1 over the alphabet size to the power q. And if we want q to be 2 and the soundness to be a subconstant function of the alphabet size, then the alphabet size must be a super constant function of the input length. We wish the soundness to be a subconstant function of the input length, and therefore the alphabet must be of size that is super constant function of the input length. Questions so far? Okay, great. Okay, so what is the state of the art in this direction? So first of all, via the parallel repetition theorem, one can get a PCP with query complexity 2 and polynomial proof length for every constant soundness. And there is also a folklore result that was firstly written in the paper of Dana and Ran. Is this right? The result via low degree curves and so on? Okay, so it says that using low degree manifolds, we can actually get a PCP of 2 queries that has soundness of 1 over polylog n and the alphabet size exponential in polylog n. And this is based on taking low degree manifolds that go through low degree extensions of the proof. And another thing I want to say is that this trade-off between the alphabet size to the soundness is not optimal, or at least we don't know it to be optimal, because as far as we know, the alphabet size may be even polynomial in 1 over the soundness, and here it is exponential. But this is what we know how to construct. And then there is the recent breakthrough of Dana and Ran that was simplified later by Rit and Prahlad that says that for every soundness we can actually get this trade-off. That is, for every soundness we can have the alphabet size equals about exponential in 1 over the soundness. And this is particularly important for hardness of approximation results. Okay, so what do we do in this work, given that this is the state of the art? Well, we show a different approach in order to achieve the folklore result, the one that says that the soundness is 1 over polylog n and the alphabet size is exponential in polylog n. And this construction, or our approach, has the feature that, first of all, in my opinion, it is simpler, even though Irit asked me to tell you that she disagrees with me on this point. But I think it is simpler. And what we both agree is that it is of more a combinatorial nature. It does not use polynomials or curves or anything like that. It just uses sampling properties of linear spaces. And actually, using in the axiomatic approach, I will show that actually we really only need sampling properties, not necessarily of linear spaces. And Irit and I believe that combinatorial proofs are usually preferable, or at least we prefer them to algebraic proofs, because we feel that they give more intuition or better explain the theorems that we prove. So we are happy with this result. And another feature of this approach is that it is based on an approach called the Derandomized direct product, which I think is a very natural approach, and it is and the fact that it can be actually realized is interesting in its own right. And hopefully this will become apparent in the second part of the talk, in which I will describe this approach. And finally, I'll mention that this is, in a way, still a work in progress. We still work on plugging our construction into the framework developed in the work of Irit and Prahlad. And if we can do that, we can actually get the same trade-off as in the work of Dana and Ran and achieve the state-of-the-art results using a combinatorial construction. Yes?
So to achieve what you just said, then you still will only need linear subspaces and no polynomial?
Yeah, yes. But I should say that while the result of Dana and Ran uses only PCPs of nearly linear proof length, nearly linear proof length, then we only get polynomial proof length. So this is still not exactly the same result. Yes?
I'm sort of a bit confused at this point because to get from the folklore result to everything, the existing proof is purely combinatorial.
Yes.
So
there is
you would say what is the problem? If you supposedly if you achieve exactly the same as the folklore result in a combinatorial.
Okay, so the folklore result only says that we have PCPs. We have PCPs, but we still need to show that we can construct decoding PCPs, so-called. Okay. Any more questions? Okay, good. So now we get to the second part, in which I'll say what this de-randomized direct product approach is, and hopefully I will convince you that it is interesting. So I'll begin with something much more basic. What is sequential repetition and what is parallel repetition? So sequential repetition is the most straightforward way of improving the soundness error of a PCP verifier. That is, suppose we have some original PCP verifier and we wish to obtain a new PCP verifier that has a better soundness, then we simply construct a new PCP verifier that invokes the original verifier for k times. And it is easy to show that the soundness decreases from s to s to the k because the invocations are independent and each has the probability of at most s to accept false claim. But it also increases the query complexity from q to k times q. And this is bad for two reasons. First of all, if we started with an original verifier that had constant soundness and we wish to obtain sub-constant soundness, then we will have to choose k to be a super constant function. And this means that the query complexity will also become a super constant function. And we don't want that to happen. Yes?
So the generic transformation from constant q to 2, so we can think of them as the same?
Okay, but this either loses the soundness or is very algebraic. This is actually the approach of Dana and Ran.
There is, but it's algebraic, so.
For higher, you can always assume that.
But it's by close versus. If you're losing it, you're willing to lose like factor of q, like soundness 1 over q or something.
Yes. If you're willing that the soundness will be 1 minus 1 over q, then you can assume that q will stay. But otherwise, if you want lower, there is no second.
There is an algebraic way that is generic and black box, sort of makes it into two queries.
Yes, but then they want to eliminate that.
And this is what the manifolds actually do. They reduce the query complexity back to 2 without losing the soundness. Okay, so this is bad for another reason, and the reason is that, as I said, in order to obtain tight hardness of approximation results, we actually want the query complexity to be 2. So even if we wanted only to have a better constant soundness, and we could choose k to be some constant, we couldn't maintain the fact that so even in this case, this technique is not sufficient. So in order to remedy those shortcomings, we have the parallel repetition. And the parallel repetition technique says, okay, so what the parallel repetition says is that instead of making k different invocations of the original verifier, we do them all in parallel. And this is done. I need to introduce the notion of direct products. So let's go to this notion. Okay, so the notion of direct product goes as follows. If I have a string w over sigma to the L, then the case direct product of w is a string that consists of all k sets of coordinates of w. That is, for the coordinates of the new string are k sets of coordinates from 1 to L, and each such coordinate contains the corresponding symbols of w at those coordinates. This is the most important slide in this talk, so you'd better not miss it. But in order to draw your attention, I'll give an example. So if the original string says 1, 2, 3.
White is a better color.
Oh, okay. So suppose it was just 1 to 4, then the tooth direct product will have symbols that contain two digits, and it will be something like 1, 2, 1, 3, 1, 4, 2, 3, 2, 4.
Will it matter that you chose L choose K, not L to the K? Or
No, it doesn't really matter, but it is more convenient to use sets than tuples. Okay, so this is how direct product goes. And jumping ahead, I'll just say that for now that when we say derandomized direct product, I mean that we don't take all the possible k subsets of coordinates, but we rather take only some of them. And this is called derandomized because if choosing a random coordinate of the standard direct product, it consists of choosing about k coordinates of the original string independently at random, then in the derandomized direct product, we choose them in some dependent way that saves us randomness. So this is called derandomized, but this is not really important for this talk. Okay. So now that we have a direct product, we can get back to parallel repetition. So what we have in the parallel repetition, we construct a new verifier, and the new verifier, given a correct claim, it expects the following proof string. We take the original proof string, the proof string of the original verifier, that convinces the original verifier to accept the correct claim. And now the proof string for the new verifier will be the case direct product of the original proof string. And now every query to the new proof string emulates Q queries to the original proof string, because it consists of K symbols of the original proof string. And using Q such symbols, we can actually simulate K times Q queries that is the symbols of Q of K invocations of the original verifier. And to say it in a little more detail, the new verifier will invoke the original verifier for K times, and then it will take the K first queries of the K invocations. That is, each one of the invocations has a first query. Then it will take all such first queries and get this K set and ask the new proof about it, and the same for the second queries and so on. Okay. So now, suppose that we are given, so let's see what we can say about the soundness. So suppose we are given some false claim and some proof for the new verifier. And let's suppose for a minute that we can always assume that the new proof string is indeed a case direct product of some proof string of the original verifier. Then in such case, it is easy to see that the parallel repetition simply simulates the sequential repetition. And so the soundness decreases to S to the K, and the proof length increases from L to L to the K, because we take all the K subsets of symbols of the original string. However, if we wish, note that if we wish to take K to be super constant, then this means that the proof length will be super polynomial. So we still cannot use it to obtain a sub-constant soundness. We didn't earn anything that allows us to gain a sub-constant soundness. We only earned something that allows us to maintain a query complexity of 2 while getting a constant soundness. But this means that if we somehow manage to derandomize the parallel repetition, to use derandomized direct product instead of the standard direct product, so that the proof length will not decrease from L to L to the K, but to something smaller, then we might be able to choose a super constant K that and still get away with it with polynomial proof length. And this is what we aim to do in this talk.
Fage and Killian had something to
Yeah, you were
can-
talking about it.
Yes, but unfortunately I don't know the results, so I can't say exactly how do we bypass it, but I think it's okay.
Yeah,
We'll get to it, I guess. So, okay, but before we get to that, let's recall that we had this strong assumption that the proof string is always a K direct product. And we cannot really make this assumption because nothing in definition of the PCP forces the prover to give us a case direct product. Well, in this case, if the proof string is not necessarily a case direct product, we have the parallel repetition theorem that says that the new verifier still accepts if probability that drops exponentially with K. That is, the soundness still drops exponentially with K. But the proof of this theorem is much, much more complicated than the simple argument we had before that the soundness decreases to S to the K. And therefore, it will probably be very difficult to try to de-randomize this proof.
So that's the fake Killian.
But it is a setting. It's
I don't want to say impossible because, for example,
they axiomatize a setting where it is impossible.
yes, but
They bypass it.
for example, you can think of Irit's proof of the PCP theorem as a kind of de-randomization. But
in the range of parameters of the
okay, so I don't like to say it's impossible, but it is supposed to be very difficult.
No, so difficult.
No, it's worthwhile saying that it's impossible in a certain setting. The Fage and Killian formalize a particular approach to the randomizing runs result.
Okay,
Where it is impossible, it does not exclude other directions of the randomizing.
okay.
Then what is the
It's yeah, I don't want to.
But
go into
the
that.
way you bypass it
It's very
seems that you add an additional way to test the
Exactly. This will be probably the.
Yeah.
Okay, so let's see indeed how may we bypass this problem, and the solution is simply to force the prover to give us a case direct product. And this can be done by using a direct product test. That is, we will use some test that will test that the string we got from the prover is a direct product, and if it will say that it is not a direct product, we will reject. So if a prover will want to convince us, he will have to provide us with something that at least looks like a direct product in a way. And such a direct product test was indeed suggested and analyzed in a sequence of papers. The last of them is by Russell, Valentin, and Avi, the IKW paper. And not only that they analyzed the direct product test in this paper, they actually managed to use this idea of using a direct product test to construct a PCP that is to simplify the parallel repetition using this test. So this gives some sort of much simpler parallel repetition-like theorem. And this is, as Boaz said, this is actually where we bypass the Fage-Killian result. They assume that we do not do something like the direct product test.
So with some probability you will do this test, and otherwise you will do the original test? That's
No, such a thing will not allow us to get a subconstant error. I will say in a few seconds what do we do, but the idea is to do them the same time using the same queries. Okay, so the IKW did construct a PCP using a direct product test, and not only they did that, they also suggested the notion of de-randomized direct product, which is what we aim for because we wish to de-randomize the parallel repetition. And they showed that this notion of de-randomized direct product can also be tested using a direct product test. But fortunately for us, they were kind enough to leave work for other people, and they did not construct a PCP using this de-randomized direct product. So this is what we do in this work. We construct a PCP based on the derandomized direct product test of IKW, and therefore we obtain PCPs of subconstant error.
But with a super polynomial alphabet.
Super constant, you mean? Oh yes, super polynomial, right? The same result, the same folklore result, yes.
So you're just to clarify, IKW did give for every fixed epsilon 2-query PCP of soundness or epsilon.
No, oh, actually yes. This would be correct. Yeah.
But not projection.
Not projection.
Yes.
No. So it's like Ram's result, but without projection.
But probably your result can be modified a little to obtain projection test.
What?
Because we can get Weizmann mismatch, which are projection.
We can get mismatch, right? Yeah.
So they have
But we did right.
I think so.
You didn't
I
try.
thought we. No, maybe we did.
We have
Somewhere.
I think it should be possible to make some small modification and obtain it, but I don't.
So projection we can, unique we cannot.
Unique we cannot. Yes.
Yeah.
Okay, so after this long introduction, let's go to our construction.
So is it a black box? Any derandomized test would give you a PCP via your...
I will say I'll say more about what we need later. But it does not suffice that we have the randomized direct product test. We also need that doing parallel repetition will not harm the operation of the direct product test. So
There was a derandomized direct product test. This we did. What we couldn't do is combine it with the PCP test.
okay, so now let's get to the construction. But before that, I want to make one more slight detour. I'll say before that this part will have 3 parts, 3 subparts, and we'll start by explaining how do we construct a PCP based on a direct product. This will not exactly follow the IKW construction. We will use a different construction. And then we'll show how to construct a PCP based on a derandomized direct product. And the main ingredient, or the most interesting part of this construction is the use of de-Bruijn graphs. So I'll explain this in the 3rd part. But before we do all this, I want to make one more detour and talk about constraint graphs. So constraint graphs are a different way to look at PCPs. So recall that we are interested only in verifiers that make 2 queries, and such verifiers can be easily viewed as graphs or naturally viewed as graphs as follows. We view every possible coordinate of the proof string as a vertex in the graph. And so a proof string corresponds to some assignment that assigns symbols of the alphabet to vertices of the graph. And now every possible test that the verifier may make makes 2 queries to the proof string. That is, makes 2 queries to vertices of the graph. So we put an edge between those 2 vertices in the graph, and we identify the test with this edge. And we say that the assignment satisfies the edge if the corresponding proof string passes this particular test of the verifier. Otherwise, we say it violates it. And now an invocation of the verifier just corresponds to choosing a random edge in the graph and checking whether it satisfies the assignment. And finally, a correct claim now corresponds to a graph that has a satisfying assignment, a graph that has some assignment that satisfies all the edges. And the false claim corresponds to a graph for which every assignment satisfies at most S fraction of the edges. So in this talk, I will switch without warning between the constraint graph view and the PCP verifier view. But one tip that can help you is that I always wish to construct a new verifier based on an original verifier. So the original verifier will always be viewed as a graph, while the new verifier will always be viewed as a PCP verifier, as we did before. Okay, so and now in this framework, the parallel repetition can be viewed as follows. What the new verifier does is to choose k random edges of the original graph, and then it queries the oracle on the set of left endpoints, this is a k set, and on the set of right endpoints, which is another k set, and it checks that the answers that it got satisfy the edges. And now we can finally get to the construction. So what is the natural, oh, sorry, before that we need to also to say what is the direct product test. What is the direct product test? The direct product test says given some string pi that we wish to test that it is a case direct product. The coordinates of the string correspond to some k sets, to a family of k sets. And the test chooses two random k sets that have some large intersection of, say, size k1. And then it checks that the answers it got agree on the intersection of those two sets. Is this clear?
It's the only thing you can do with two queries.
I guess so. Okay, so indeed the series of papers that analyzed this test showed that if the proof string is far from being a direct product, then the test rejects with high probability. And here the meaning of far and high probability improve from one paper to the other.
By the way, isn't this also roughly like what Feigen-Killian did?
Yeah.
Okay.
Produce sort of
Yeah, that's also.
I guess it's roughly like that.
Yeah. But the random things are the noise, are they confused and
Okay, it's really easy. Okay, what they did is a PCP, so it's not exactly that, but it also depends whether you consider the confuse or compare or the miss and match. I don't know.
There is a relation. It should be complete.
There is some
Yeah,
relation.
they don't have direct product directly. It's implicit in what they do.
Yes.
They just do it.
But their intuition is also very different. They're actually not thinking about direct product testing.
yeah.
Yeah,
Yeah,
but
but
generally,
it is similar.
if the edges were like loops or something, then it would be like you choose K1 loops, and then you choose also, you give to the one prover the
Right.
K2
I mean,
one.
implicitly, it must be their product. I mean, it just says, you know, implicitly in the PCP term there's property testing. I mean, it's not stated.
Okay, so now what is the natural way to combine parallel repetition with direct product test? I think that the most natural thing to do is just to combine the left query of the direct product test with the left query of the parallel repetition, and the right query of the direct product test with the right query of the parallel repetition. I'll say it more formally in a second. And as I said, this is somewhat different than what was done in the IKW work, which was unnatural.
You can bypass the natural.
Yes, this is true.
Wait, so what's the test? Those are some completely distinct queries.
No, we have one query that contains the k set of the direct product test and the set of the left endpoints of the parallel repetition, and one query that has both the k set, the right k set of the direct product test and the
What I'm
set
saying
of
is
right
that those
endpoints.
sets are independent and therefore very likely disjoint.
Probably, yes.
So if like the graph had like also self loops, then you could say that you're doing Feigen-Killian, but also have like the self loops that correspond to the.
Maybe. Okay, so in this talk it will be actually more convenient to look at this way. This is just an equivalent way of viewing this construction. So this view will say as follows. First we choose a random set of edges, and then we choose two k sets at random under the condition that they intersect on some large intersection, and one set contains the left endpoints and the other set contains the right endpoints. And somewhat more formally, it will be as follows. Given a graph and a proof, we choose some set of, say, k0 edges, and let C1 and C2 be the sets of endpoints, and we choose a random set of K1 vertices, which will be the intersection, and then we choose two random sets, B1 and B2, that contain the union of A and C1 and the union of A and C2, respectively. And then we check that the proof at the coordinates B1 and B2 agree, those two coordinates of the proof agree on A and satisfy the edges in the set we chose, the set E0. And indeed, it can be shown that if the graph G has constant soundness, then the probability that the test accepts decreases exponentially with K0. And here I want to say two additional things. First of all, this is not true for any choice of K0, K1, and K. Once we have chosen K0, the choices of K1 and K are determined. And the other thing is that just that the assumption that G has constant soundness is just to make the presentation slide shorter, but we can actually have a result for every possible soundness. Okay, so
What K1 and K in principle could be O of K0?
No, K has to be quadratic, at least in
Yeah.
the analysis that we have. K
yeah,
has to be quadratic. K1
so
and K0, but
K1 and K0 will be about the same size, and K will be quadratic in each of them.
Is this due to analysis or due
yeah,
to
analysis.
Due to
Yeah,
the analysis.
yeah,
counter example?
no.
This is what we know how to do, but maybe it's possible to do better. Okay, so this is all I had to say about the direct product test, or the standard direct product test.
To Boaz's question, this problem occurs already in the direct product analysis for get PCPs. You don't know how to reduce this quadratic dependency, even if you only do direct product test.
But you also don't know that it doesn't.
No, we don't know.
Okay, so but we actually gathered here today to hear about the randomized direct product. So let's look at that. So what was the de-randomized direct product test, or the de-randomized direct product notion of IKW? It says as follows: suppose we have some string W of length L, and we wish to take its direct product. So now we identify the coordinates from 1 to L with the vectors of the linear space F to the M, for some field F and some integer M. And now, instead of taking all the possible k-sets of coordinates, we take only the k-sets that form a linear subspace of F to the M, say of dimension D. So we choose some F, some M, and some D, and then we define K to be the size of a D-dimensional subspace. Okay, so now how do we do a direct product test of this direct product? Well, we do just the same as the original direct product test, but we replace each occurrence of the word set with the word subspace. So we choose two random D-dimensional subspaces that under the restriction that they intersect on some D1 dimensional subspace. And we check that the answers we get are consistent on the intersection subspace. And one of the results of IKW said that if the proof string is far from any K randomized direct product, then the test rejects with high probability. Okay, so now we have the randomized direct product test. So what's the problem with obtaining a parallel repetition, a de-randomized parallel repetition?
Yeah.
Yes,
What's the dependence on the
So how does it value this?
Polynomial.
Yeah, so okay, I don't want to get to the parameters, but it can be chosen such that it doesn't get exponential blow up in the proof length. So let's see why it is not straightforward to construct a PCP. Let's imagine the following test. I mean, this test is just what we get by just taking the previous way for constructing PCPs based on a direct product and plugging in this de-randomized direct product test. again, we choose a random set of K0 edges, and then we choose a D1 dimensional subspace A that will serve as the intersection subspace. And then we choose two D-dimensional subspaces B1 and B2 under the restriction that they contain the union of A and C1 and the union of A and C2, and check that the coordinates of pi at B1 and at B2 agree on A and satisfy the edges. And of course, the problem is that there is no reason for such subspaces B1 and B2 to exist. I mean, if K, the size of the D-dimensional subspaces, was much, much larger than K0, then it was trivial that they would exist. But such large K comparing to K0 does not give us anything. If we want K to be polynomial in K0, then there is no reason for such subspaces to exist, simply because the set E0 was chosen to be a random set of edges, and this means that C1 and C2 have no apparent structure, and therefore there is no reason for a small subspace to contain them all.
So
We
even
don't
if you
understand
chose
D is large enough.
If D is large enough, if D is at least K0, so then there is no problem. But in this case, K, the size of the D-dimensional subspace, will be exponential in K0, and this is something we cannot accept.
The subspace will be of size exponential
In the dimension.
If you want it to be polynomial.
So even if you chose C1 to be a random subspace, you'd still have C2 to be like an arbitrary set.
Exactly. This is the problem.
So in the IKW, what is D in terms of the error parameter?
So, excuse me?
The dimension. That's log of the.
Yes.
Something like that.
It's still a quadratic relation or polynomial relation between K0.
So we actually make the dimension constant, so something like 25.
Yeah, so.
D is 25 and B1 is.
Oh, I see. The field is
So
large.
The field controls the
But the error, yes, the field size is what matters, and actually the error decreases polynomially with K. Okay, so how do we overcome this problem? Then we have two steps now. First, I will show that if the original graph has some nice linear structure, that then we will be able to choose the set of edges and the sets of endpoints in a way that they will be linear spaces, and therefore the test will just go through. And then we will show that every possible constraint graph can be embedded on such graph that has a nice linear structure. So what do I mean by a graph with a linear structure? Well, first I mean that the vertices of the graph can be identified with f to the m, but this is just the same as the derandomized direct product was defined. A more important requirement is that, well, edges of the graph can be thought as pairs of vectors from f to the m. And if we concatenate those pairs of vectors, we can think of the edges as elements of f to the 2m. So I now require that not only the edges are elements of f to the 2m, but the set of edges forms a subspace of f to the 2m. And this already gives if we project the edges to either side, we get a subspace. But we need another requirement, and that is that a random subspace of the edges, when projected either to the left endpoints or to the right endpoints, give a random subspace of the vertices.
The purpose is to hide which of the queries of each player come from the
this is yes.
come from the direct product test. That's essentially important.
Yes, this is one purpose. The other purpose is if the vertices were not a random subspace, and this would mean that in the direct product test, the sets that we choose, B1 and B2, are not very random. And this would also harm the operation of the direct product test. Okay, so given those three requirements, it is now we now get this following test, which is just the same test as before, but now choosing the linear subspace of the edges, and now everything goes through as we would like it to be. And indeed, we can prove that if G has constant soundness, then the probability that the test accepts goes like 1 over K0 to some power. Now, if we...
K0 is f to the d0.
Sorry?
K0 is
Yeah.
the cardinality of
Yeah, I should have said it. K0 is just the cardinality of a D0 subspace. Now, I should say that first of all, if we knew that the proof string that we get is a direct product, and therefore if we knew that, then we could only do the parallel repetition part and not the direct product test part, then we would have expected the soundness to decrease like 1 over K0. So we don't get something that is that good just because Chebyshev inequality or something like that. We don't get something that good, but we get something that is 1 over K0 to some power that is smaller than 1, which is still sufficient for our purposes.
You should have gotten 2 to the minus K0, no?
No, it's linear. It's just pairwise independent.
Yeah,
You cannot get more than 1 over K. That's the best.
the edges are not chosen in an independent manner. They are chosen in pairwise independent manner. Yes, we could, but there is a limit to how much algebra I'm willing to put to this.
Let me point out that it's really an interesting question to do it even in the case of only the randomized, only direct product test. Forget PCP. We don't know how to do it. We try. So it's really an interesting question.
Yeah, all I'm saying is that it's true that if it's linear, then you don't expect the error to be better. But generally, you could expect the error to be exponentially small in K0.
Yeah, of course.
Even in the randomized test?
We don't know how to make it even quadratic.
Okay, so now that now it remains to show that indeed we can do this magic to embed every constraint graph.
The proof of this under this assumption is exactly the same as
Exactly the same. We just replace Chernoff with Chebyshev. Yes, this is it. Okay, so now let's show how can we embed every constraint graph on on one that has linear structure. So this is the last part, and indeed the keyword here is the de-Bruijn graph. So what's a de-Bruijn graph? A de-Bruijn graph is a layered graph. In our context, it will have polylog layers. And the vertices of every layer are identified with some linear subspace, with some linear space f to the t. And in order to know what the edges are, that is, suppose we have some vertex alpha 1 to alpha t in some layer. If we wish to know to what vertices it is connected in the next layer, we do the following process. We take the vector, we shift it to the left 1 step, and then we add an arbitrary field element at the right. Okay, usually it is done only with a field of size 2, and then it just says that given a binary string, we shift it cyclically to the left 1 step, and we either flip the last bit or not, which is a rather natural operation in, at least if you are an engineer, but I don't want to get to it. And here is a picture that I've taken from Wikipedia. It is not actually a de-Bruijn graph, it's just a layered graph, but I didn't find a de-Bruijn graph.
Why? Isn't it a de-Bruijn graph? It's just butterflies?
No, it is a Benesu network, which means that it's 2 butterflies that were sticked in the middle.
Half of this.
Yeah, each half is a butterfly graph. Okay, so so those graphs are very nice, and they were already used in the PCP literature before. And but before we see how to embed every, what we will do is to embed every constraint graph on de-Bruijn graph. But before we show how to do that, let's see that they do have a linear structure. And I will go on this in much detail because I think that this property of linear structure seems very strong at first, and the fact that there is a simple graph that has this property is quite surprising. So remember that every vertex of in each layer is already identified with some vector space f to the t. And so all we need to do in order to identify the vertices of the whole graph with the vectors of a linear space is just to combine the layers into one linear space. And this is done by taking f to the m with m equals t plus 1. So each vector gets an additional element. And this element will be used to say in which layer we are. And we will denote the layer we are in using powers of the generator of the multiplicative group of the field. That is, if gamma is the generator of the multiplicative group, then the vertex alpha 1 to alpha t in layer I will be gamma I, comma alpha 1 to alpha t. It is now easy to see that the edges of the graph are a linear space because let's see what constraints should the vector of f to the 2m need to satisfy in order to be an edge. Then it needs to satisfy equality constraints between alpha 2 to alpha t here and alpha 2 to alpha t here. And this element needs to be gamma times this element. And both constraints are linear. So it is a subspace. And there is also the other third requirement of graphs to have linear structure, but it is not that interesting, so I won't go over it. I'll just say that if someone thinks that taking the generator of the multiplicative group is an algebraic step, then I'll say that it could probably have been replaced by just taking, multiplicatives of 1. That is just to put here I and use some field of some large characteristic. And this would use affine spaces rather than linear spaces, but it is not that interesting. Yes?
What was the other requirement that you take
Projection on each side is a full subspace.
If you take a random space of edges, then the projection to each of the sides of the endpoints is a random space.
You never get 0 in the first coordinate, but I guess you don't care about it.
No, I don't really care about this.
It's a point. It's not exactly a subspace, but it's, you don't see it.
No, I can just say that I have vertices of the form 0, alpha 1 to alpha t, but I don't use them. Okay. So, now the crucial property that allows us to embed constraint graphs on de-Bruijn graphs is that de-Bruijn graphs are routing networks. And what this means is that if we think of each vertex in the network as a computer and of the edges as wires that connect the computers, so computers that are connected by an edge can communicate with each other. And we consider a case in which every computer in the first layer wishes to send some packet to some computer in the last layer, such that no two computers wish to send a packet to the same computer. Or in other words, the mapping of source computers to target computers is a permutation. Then we can find vertex disjoint paths that connect source computers to target computers.
That's true for the Benes network.
Yes, this is true for the Benes network as well.
No, not for the de-Bruijn graphs.
What? No, this is also true for the de-Bruijn graphs.
Not for GF2 anymore.
No? Okay. Because I
That's
think
what
that
I remember from my parallel computation course.
really, I think that if you take maybe few copies of the de-Bruijn graphs concatenated, then it is true.
One after the other.
Yes.
Oh yeah, that's
You need another. You need about 5 like this or 6 like this. But I try to avoid the disability here. But okay, so yes, so we can find vertex disjoint paths from source computers to target from computers for every possible such mapping. And this means that if the computers route the packets along those paths, then every computer in the network only has to deal with one packet. Dana, is there a problem?
No, I was bothering.
Oh, okay, so it's not that something is wrong with the slide. Okay. Okay. So how do we use this property to embed constraint graphs? Well, suppose that we have some constraint graph, and first of all, without loss of generality, we can always assume that the constraint graph has a constant degree. This is using standard PCP techniques. And let's assume as a warm-up that the constraint graph has a degree 1. That is, every vertex has only one edge connected to it. So now what we do is to identify the first layer with the vertices of the original graph, and the same for the last layer. And now we find the vertex disjoint paths from each vertex of the original graph on the first layer to its unique neighbor in the graph on the last layer. And after we find those vertex disjoint paths, we embed the edges on those paths.
Is this also Spearman's technique?
Sorry? Yeah, yes. This is exactly all the previous techniques.
All the previous?
Yes. Yeah, I think I should have said it. Yes, this was the same that was done in Polishuk-Spielmann work and in the BJHSV and in the Harsha Sudan and all the other PCP works. Yes, but okay, there is one small difference that they embedded circuits and we embed constraint graphs that already have gap, but okay, their constraint graphs did not have any gap, and they did it as a starting point in order to achieve some gap. And we start with some gap, and we just want to have some nice structure. But it is not any major difference, right?
Sanjeev just wants some credit to the original people who put the de-Bruijn graph in the PCP.
Yeah, I agree.
So that's Polishuk.
Yes.
And if you had the soundness constant, you will have soundness 1 minus 1 over polylog.
Excuse me?
If you started with soundness that is constant, you'll have now soundness that's 1.
Yes, not exactly. I'll have rejection probability over polylog, but before I get to that, I just want to say how do you embed the edges on the vertex disjoint paths, because I haven't said it. So suppose that we have some vertex disjoint path E1 to EP, and we want to embed some edge of the original graph, bold E, on this path. So what we do is we put equality constraint on all the edges of the path except for the last one. So this will route the value assigned to this vertex of the original graph up to here. And this is the unique neighbor of the original vertex. And now we identify the constraint of the edge bold E with this edge, with the last edge in the path. So, no, it does not. Because it does, sorry? It does not preserve either projection property or unique game property, just because there are edges that we do not use in the routing, right? And they become trivial constraints.
So you don't just erase them? I don't.
Yes, but I want to have a de-Bruijn graph. I want to have linear structure. If I erase those edges, I won't have linear structure anymore.
But that's the only reason why it's not.
Yes. So is this clear?
Wait, so you also lose in the soundness?
Yes, I will get to this point in a second. Okay, so now, so far I assume that every vertex has only one edge, but if we have some constant degree graph, then we just repeat this process a constant number of times. And now we think of it as routing some constant number of packets at the same time instead of from each source to each target. But this is really does not matter for the purposes of the construction. And the last thing.
You can have I mean, two of the paths from the different parts can overlap.
Yes. So now I will use the same edge for in the de-Bruijn graph to embed two distinct edges in the original graph. But at least as long as this is a constant number, this construction can still go through. Just use a larger alphabet and so on. It's not really interesting, but as long as this is a constant number of edges, or even a poly-logarithmic number of edges, this can be done.
Whatever it is, you're going to lose it in the soundness.
Yes, but this is true even if I have a constant degree, this is still true. But so okay, so indeed, as Dana and Boaz said, we lose in the soundness, so the original rejection probability is decreased by a factor, by a poly-logarithmic factor.
The poly-logarithmic is the size of the field.
Yes, it's just the length of the parts. The reason is just that since every edge was embedded on a path of poly-logarithmic length, now if we wish to mess up this edge, it suffices to mess up only one edge along the path. So
also all the edges that do not participate in the
yes, and we also have those edges.
So for this you need the de-Bruijn construction is like a very efficient construction. The number of edges is very small.
Yes,
So you use one
okay. So now, yes, you're right. But
it is, but you should say that. It's not. It doesn't work for any de-Bruijn path. Only for de-Bruijn paths that are very efficient.
no, what do you mean? Yes, of course. I could have used the de-Bruijn graphs that are very inefficient, but then they wouldn't be useful also for other reasons. But okay, so so just to say what happens here, since we deal with the soundness and not with the rejection probability, we get a slightly uglier formula, this formula. And this means that even if the soundness was very small at the beginning, now it becomes very close to 1. But this is something we can actually afford, because recall that the next thing we wish to do with the constraint graph is to apply some derandomized direct product or derandomized parallel repetition, and this process will make up for the loss in the soundness. Okay, so this is about it. I can finish here, or I can discuss the more general approach.
Wait, so, but then the parameters are what? So how many random bits for what sound?
Okay, so I discussed the randomness. I discussed the proof length instead of the randomness, but the same. But the randomness will just be about log of the proof length. I mean.
The proof length will be polynomial.
Oh yeah, this is the problem. Yes, yes, I didn't say anything about the choice of the parameters, but you can choose the parameters such that the proof length will be polynomial.
You exactly recover this folklore result.
Yes, exactly.
Wait, no.
Without the derandomized low degree test.
Because the subspaces that will be chosen eventually will be of constant degree.
Constant dimension. Yes, what will be large will be the
field size, it will be poly-logarithmic, and that's
No, but how does that soundness of close to 1?
you take k to compensate for it. So
So
you
K is
take k will be bigger polylog, yes. And it determines the field size.
I see. So the field size is part of it. That's part of it.
Okay, so we'll finish here.
So what is the length of the actual axiomatic approach?
Uh,
Maybe you want to just advertise it and
Okay, exactly. Okay, so we'll do this. So So when I say axiomatic approach, let's see in general what do we mean for what do we need in order for this to work. And okay, one thing I should say before, the whole idea of this axiomatic approach, so-called, is that well, we actually got the derandomized PCP just by taking the original PCP and replacing each occurrence of the word set with the word subspace, right? So this calls for trying to find some unified framework that both constructions will be special cases of. So this is actually what we do. And what we need for this approach, so what we actually need in general to have is some distribution from which we choose the set of edges, and some distribution to choose the intersection set, and some distribution to choose those larger sets. And given those distributions, we have 4 simple axioms, natural axioms, that if those distributions satisfy them, then this construction works. So first of all, we need a random set of edges drawn from the distribution to have a good chance of detecting error, or in other words, that a random set of edges will sample well the set of all edges. And this is clearly a necessary requirement, because if it doesn't hold it, even sequential repetition using those sets of edges won't work. And then we need to have a direct product test that works with this distribution on intersection sets and on large sets, even without the edges. And this is also needed for our approach, because we wish to base ourselves on the direct product test. And then we need this is a more cumbersome requirement. We need that if we choose a random set of endpoints according to the distribution of the edges, and then restrict the big sets, the B1 and B2, to contain those endpoints, then they are still sufficiently random. And this sufficiently random actually means sampling. That is, if we consider the collection of all sets B1 and B2 that contain both the intersection set and the left endpoints, and we also consider the collection of all big sets B1 and B2 that just contain the intersection set, then the first collection samples well the second collection. And finally, we just require that given some big set B1 or B2, one cannot deduce the set of the endpoints of the edges that were used to choose the set B, because otherwise the prover could have just lied on those endpoints and say the truth on all the others. Okay, and this is really it now. Oh, okay, so we also have summary that we get.
What's the axiomat? What was the automatic axiomat?
So, okay, so those are probably necessary axioms, and yes, and whenever we have it, we have the randomized direct product construction of PCP, and whose error depends on the sampling error of those axioms. And okay, so getting to the.
Given B1 cannot reduce the set of endpoints.
Okay, what I mean is that fixing a set B, B1 or B2, and fixing an intersection set, and now considering a random set of endpoints under the conditioning.
B1 and B2.
Yeah, we fixed B1 and B2, and now we think of a random set of edges under the condition that the sets of endpoints are contained in the sets B1 and B2. Then the sets of endpoints sample well the sets B1 and B2.
The set of endpoints samples.
Maybe it will be easier to tackle offline, because I think.
Given B1 and B2, you know what the edges are.
No.
No, that's the whole point. If the the verifier could tell which, I mean, if the two provers, so you get.
Okay, if we know both B1 and B2,
Which were the edges?
Avi. Avi, if you know both B1 and B2, then it might be right. But since we are in a two-prover setting, each prover knows only one of the sets, B1 or B2.
Both B1 and B2.
Right. I mean either B1 or B2.
Okay.
But okay. Okay. So now for a summary of the talk, so we construct the folklore result of sub-constant error 1 over polylog n and alphabet size exponential in polylog n. And we use a direct product approach, which goes by testing that the proof is a direct product and then performing parallel repetition. And we can actually pull this out with a derandomized direct product. And this is done by showing that the test can be performed for graphs that have linear structure, and showing that de-Bruijn graphs have linear structure, and that every constraint graph can be embedded on de-Bruijn graph. Okay, now this is it. Thank you.
This is more of an observation than a question. So at different points you were trying to say, is this algebra or is it combinatorial? I think one difference one way of formalizing this, maybe I'm not getting it right, is that you look at where the algebra is happening. Okay, so here you're doing algebra on the coordinates, but if you look at what the values of the proof are, for a valid proof, the values of a proof are just projections of the old values. You're never even taking linear combinations of old values.
Yes, but right.
So whereas any kind of coding, so a lot of the other constructions are you take the proof and you look at a coding of the proof under some linear code, and so the values for a valid proof are supposed to be linear combinations.
Yes, but I would have probably been happy also with some coding construction that would use a general code, not particular low degree code.
So OR doesn't want to not be allowed to use codes.
Yes.
This is
But you don't use them.
Uh,
Yeah.
But in everything,
But he wants a
it's
license
just one
to
set.
use it.
Yeah.
Oh, I would have been happy to use a general code. I just don't want to be restricted to use polynomials. Ariel, you also had a question?
So you said your graph needed a few properties, and one property was that if you choose a random subspace, then the edges going out of it.
No, if I choose a random subspace of edges, and I project it to endpoints.
And the endpoints are a random subspace.
Yes.
And you were saying that the de-Bruijn graph has that property too?
Under the linear structure that I defined. Actually, this is not exactly this property because the dimension of the subspace of vertices may be slightly smaller than the dimension of the subspace of edges, but it is essentially that. But essentially, it has the property.
More questions? Okay, thanks. Just a couple of comments. First of all, today too, there's a member seminar, and I think this is the best chance for anybody who wants to hear about the fundamental lemma.
Hmm.
That we think in automorphic forms, that's like,
Oh. Yeah.
This is false.
Yeah. This is false?
So set to be large enough to query the whole proof.
To query.
You just have an NP proof, and this is 0. This is not 0.
the second is that Dana
First of all,
and
yours
Ev
has
and
these different
maybe others.
So how
came
does-
from over Wolfram.
You're right.
I've seen this many places. I don't know why it's got false.
Yeah, you're right. I'm trying to think. I can tell you where does it come from. Yeah, exactly.
I don't see a way to.
Yeah, I need to think why it falls, but you're right. I didn't think of it. Thanks.
Tomorrow right after lunch? Okay, tomorrow after lunch. Good.
Someone knows how do I get out from the full screen mode? if I have a keyboard here.
מה?
איך אני יוצא מהפול סקרין? יש פה איזושהי מקלדת?
כן, הנה. מתחת
אוקיי.
לזה.
אוקיי.
טוב, זכית בפרילנס. זה
תודה.
הנוהל.
אתה יודע רק איך אני מנתק עכשיו את ה... דיסק-און-קי? כן.
לא יודע, אני בוא תלך לאפליקיישנס. משהו.
remove? לא, זה בטח יהיה remove לאפליקיישנס. לא, זה לא מה שאני רוצה. היי. בסדר, מה נשמע? תודה רבה.
כן, היה ממש מצוין.
הייתה לי הרגשה שהלעיתי אנשים, אבל...
לא, זה היה קצב ממש מצוין.
תודה רבה.
יש לי כמה הערות קטנות, ממש...
אני אשמח.
רק שנייה.
אולי... כן, אולי זה כאן, כפתור ימני, אולי...
יכול להיות. רואים את זה? הנה, הוא מעוטה, הוא מעבב, אני חושב שאתה יכול להוציא אותך.
אתה חושב?
כן.
טוב, ניקח את הסיכון, אני כבר... לא, פשוט עברנו מסך, אבל נו, המון פעמים הוצאתי אותו בלי לעשות safely remove.
ולקחת את שלך, זה לא...
כן, תראה, תמיד יש פעם
כן, זה שלי.
שניים...
כן.
מה הלו"ז שלך להיום, או מה אתה...
אני אצטרך לעוף מפה בסביבות 4:30, 5, כי יש לי טיסה לתפוס ב8 בניו-יורק. תודה.
נכון, אתה רוצה לבוסטון.
כן.
ואתה באינסטיטוט, אתה לא מגיע לפרינסטון
אני
תבוא איתו ללאנץ' ודבר
כן.
איתו ותדבר איתו אחרי זה. איפה המחבר שלו? אני לא רואה את ה... מה, תגיד, דלית כבר עוזבת, אנחנו בקושי ראינו אותה.
היי אור.
היי.
מה נשמע?
בסדר, מה נשמע? לא ידעתי שאתה פה.
כולם פה.
אז למדת משהו.
מה שקורה שאני לוחץ על זה,
לא ראית לאן...
אני לוחץ על האינטרלינק הזה.
מה לא, זה לא חושב שזה... לא, זה סוג אחר של רימוט. אני לא מבין לנו נעלם. שמת את זה גם תפריד.
איזה רימוט?
הרימוט שמחבר את ה...
אולי זה זה?
I don't see the remote to turn this on.
Oh, I have it right here.
You have it? Okay, so you can do it.